Hey everybody. Today we're looking at graphs of sine and cosine functions. Y equals sine x and y equals cosine x both look like waves. The maximum values are 1 and the minimum values are -1. And the only real difference between these two graphs is that sine x starts at 0, 0 and cosine x starts at 0, 1. You'll hear the catch-all term sinusoidal to describe graphs that have this sort of shape. Two important features to notice right off the bat. Cosine of x is an even function. It's symmetric about the y-axis. If you replace x with negative x, the y value doesn't change. On the other hand, sine x is an odd function. It's symmetric about the origin. And if you replace x with negative x, the y value changes from positive to negative or negative to positive. The other thing to notice is that both of these functions are periodic with period 2 pi. That is, they start to repeat themselves after 2 pi units. If we need to plot specific points on these graphs, we can do so by remembering our unit circle trigonometry. Any angle theta can be drawn in standard position, and then that'll pick out a unique point x comma y on that unit circle, x squared plus y squared equals 1. Once you do that, the y value of that point is the sine of that angle, and the x value of that point, the x coordinate of that point, is the cosine of the angle. For instance, for the angle pi over 3, we get x equals root 3 over 2 and y equals 1/2. So the sine of pi over 3 is root 3 over 2, and the cosine of pi over 3 is 1/2. Let's start looking at more complicated sine and cosine functions, starting with by seeing what happens when we just put a constant multiple in front. When a is greater than 0, the graphs of a sine x and a cosine x represent just vertical stretches of those basic sine and cosine functions. So here, for example, I've drawn y equals sine x in blue, y equals 1/2 sine x in orange, so that's crunching it down by a factor of 1/2, and y equals 2 sine x in black, stretching the graph vertically by a factor of 2. Notice that the maximum heights of the graphs are 1/2, 1, and 2 respectively. So really just the value of that a in the case where a is greater than 0. The vertical distance between the middle of a sine graph or cosine graph and the maximum is called the amplitude of the graph. The amplitude of a sine x and a cosine x is going to be the absolute value of a. So we're throwing away a negative sign if there is one there. So what happens if a is negative? In that situation, the function y equals a sine x or y equals a cosine x also incorporates a vertical flip. The amplitude's still the same, the absolute value of a, but now we have a vertical flip, a reflection over the x-axis. Here's an example. I have graphs of y equals 2 sine x and -2 sine x, 2 sine x in black, -2 sine x in orange. Both of these graphs have amplitude 2. Amplitude should always be a positive number. All right, so what happens if we put the constant multiple on the inside of the function? Y equals sine bx and y equals cosine bx incorporate horizontal stretches and compressions. It's going to be a stretch when that constant is between 0 and 1, and a compression if b is greater than 1. The period of either of these functions is going to be a little bit different, not just 2 pi, because you've stretched or compressed. And in fact, the period is going to be given by 2 pi divided by that constant b. So here's some examples. I've again drawn y equals sine x, this time in green. Y equals sine of 1/2 x is going to be in blue, so that's a stretch because b is between 0 and 1. And y equals sine of 2x is in red. That's going to be a horizontal compression because that constant b is greater than 1. The frequency of a sine or cosine function is the number of times the function repeats itself per unit. Since period is the number of units that pass before the function begins to repeat itself, frequency and period are reciprocals of one another. So if period is 2 pi over b, then frequency is b over 2 pi. So, for example, in this graph, we can see that we have a period of 4, and therefore a frequency of 1/4. While we're at it, let's notice that the amplitude here is 2. That's the distance between the center of the sine graph at y equals 0 and its maximum value at y equals 2. Now we can actually write down a possible equation for this graph if we like. Using the fact that the period is 4 and solving 4 equals 2 pi over b, we get b is pi over 2. Since the amplitude is 2 in this case, and there does not appear to be a vertical reflection, we can say that a is 2. Overall, we get y equals 2 sine pi x over 2. We can also incorporate horizontal shifts into any of these graphs by replacing x with x minus c. That's the case for any function. Replacing x with x minus c is going to constitute a horizontal shift. This is going to move the graph to the right when c is positive and to the left when c is negative. Let's have a quick summary of how to sketch sine and cosine functions. If you have y equals a sine b times the quantity x minus c, or a cosine b times x minus c, you get an amplitude of the absolute value of a period of 2 pi over b, and a horizontal shift of c, being to the right when c is positive and to the left when c is negative. If a is less than 0, the graph also incorporates a vertical flip over the x-axis. Let's wrap up by doing one complete example. Graph y equals 1/2 cosine pi times the quantity x minus 1. So in this case, a is 1/2, b is pi, and c is 1. So the amplitude is going to be 1/2. The period, 2 pi over b, is going to be 2, and the horizontal shift is going to be 1 unit to the right. Here's what the graph looks like. I've graphed this by starting at x equals c, so that's at x equals 1, and starting at a maximum height of y equals a, here 1/2. I know that cosine starts at its maximum value. The period of 2 is going to be the distance between peaks. So if I'm starting at a peak, I need to also end at a peak. So from peak to peak is going to be from 1 to 3.